a copy of his presentation to everyone. With further ado, Andy, you took over, please.
Okay, hopefully you can see my screen. Is that correct? Great, perfect. Well, I'm an engineer and I can't talk without slides. And so I have a PowerPoint briefing to kind of guide the discussion today. What I'm hoping is that my presentation will stimulate thoughts on your part and you'll ask me questions or make comments. So I'll try to pause, but don't be afraid to interrupt me. I don't mind being interrupted and excuse me? I think that's someone talking to their kid.
I just need everyone.
Don't worry, but feel free to don't make them muted. I want to let them unmute themselves if they want to interrupt and ask me a question. You could put it in the chat, and then I'll pause and I'll allow you to ask a question if that will work better. Professor Hamadar, is that the best thing? Oh, you're muted now.
I believe they can unmute themselves when they
Okay. Each system works different. As long as they can unmute themselves and interrupt me, that's great.
If for some reason you can't, all the participants, I'm going to put everybody on mute, but if for some reason you can't, send me a chat and I will unmute you.
So anyway, I'm going to talk today about the operational integration of autonomous aircraft. I'm not going to talk about how to build an autonomous aircraft. I'm going to talk about how we might be able to make them so that they can operate in the airspace system. Yes, there we go. So first of all, over 200 years ago, we all know the date, December 17th, 1903, that the Wright brothers achieved the first manned flight, actually powered manned flight. The real achievement was it was a manned flight. And for the next, 100 plus years, aviation evolved centered around the fact that there was a human pilot on board the aircraft, flying the aircraft. When we think about unmanned aircraft or autonomous flight, we break the paradigm, especially the operational paradigm of how these aircraft fit into the airspace and play nice with other aircraft in the system. So really the next frontier in aviation is autonomous flight. We talk about the jet age as being a frontier in aviation. A lot of people talked about the information age as being an era in flight, GPS being part of that information age. But really the next kind of iteration of the information age is this autonomous flight age. And I show a bunch of aircraft here that are in one way or another semi or almost fully autonomous. But it's not just the aircraft themselves. It's the entire ecosystem is becoming more and more automated, from air traffic control, how we manage the ComNav and surveillance systems, everything associated with flight. Airline operational control is becoming more and more automated. When I first started working with airlines, for example, a dispatcher would dispatch, 30, 40 aircraft in a shift. 10 years later, a single dispatcher, because of automation, was dispatching 80 aircraft in a shift. And we're seeing more and more of automation changing the nature of work for the human decision makers involved in the system. And I show a range of aircraft, both military aircraft that are operating today, and aircraft that are really close to operating in the near future. And I'll pause here to see if there's any questions or comments. So a little bit of terminology. I'm going to try to be anyway, really disciplined. I'm going to use the word automation to be kind of a holistic term to apply to things that are automated and things that are autonomous. And I'll say what the difference is in a second. But increased automation we're definitely moving in that direction to where we're having increasingly autonomous systems. Doesn't mean everything is fully autonomous. Now, what's the difference between automated flight and autonomous flight? The ICAO, I'm assuming people are familiar with ICAO. That's the International Civil Aviation Organization. It's essentially a body of the UN that is the treaty organization that sets the standards worldwide for aviation. They have a very strict definition of autonomous flight, and I'm not going to use their definition. I'm going to use the definitions that were developed by the ASTM, which is a standard body. Automated flight is a flight that follows a very predefined set of instructions, and usually will fly a very predetermined path. Even with a bunch of contingencies, it's very much defined exactly what will happen. Think if-then statements. And it does this without necessarily human intervention. A human might monitor what's going on, but the human is not needed to operate the aircraft. The aircraft can do maybe a limited set of functions in a very automatic fashion. And a good example of this is the Cat-3 landing system. For those of you who aren't familiar, I'll show a Cat-3 landing in a minute. But a Cat-3 landing system, the aircraft follows a very well-defined path right to almost the touchdown point on the runway. And the pilot doesn't do anything. Matter of fact, they can't do anything. They can't even adjust anything slightly. They only can do one thing, and that is abort the landing and do a go-around. So the human's role is, as a monitor and an overseer of the operation, is really to abort the operation. Contrast that to autonomous flight, and that's a flight that also does not require a human being, but that the decisions and the solutions and the outcomes are not predefined, and they're independently determined based on the situational information available to the automation. And so it can behave in the absence of a predefined plan. And a good example of this is a system that was developed by the US military called ACIS. And I can't remember what ACIS stands for, but you could probably Google it. ACIS is a automated landing system for rotorcraft that was developed for cargo rotorcraft, and the human defines kind of a general landing zone, and then the aircraft dynamically chooses the path and the exact touchdown point based on information it gets from the sensors, including the location of trees and other obstacles like wires, the location of things on the ground, and even the terrain of the ground. It will pick the exact landing point and the path the aircraft will take to the landing ground. And each time it executes that landing, even with the same defined landing zone, it might be slightly different because the circumstances might be slightly different at the time. The Cat-3 landing system, that aircraft, as a matter of fact, you might have seen photos of time-lapse, long exposure photography of aircraft flying into an airport with the head, the landing lights on, and they just overlay each other because the aircraft follows the same exact path to the ground each time. Now, I want to contrast that from an unmanned aircraft. An unmanned aircraft is an aircraft that doesn't have an onboard pilot. It doesn't actually have to be automated at all. An unmanned aircraft could include an aircraft that's fully remotely controlled or teleoperated. It could have very little automation on board, but that's different than an automated or autonomous aircraft. Just for an aside, ICAO defines an autonomous flight as a flight where the human has no ability to intervene. And I don't think anyone is talking about an aircraft that will not accept instructions from a human being at any point. So this is a video. On the left is a video of a Cat 3 landing. You can see that the out the window, you can't even see the runway. The aircraft's going through the clouds, following a very, using sensor information. It's flying a very predetermined path. And the first time you see anything out the window, the aircraft's practically on the ground. And that's why we have a Cat 3 landing system, so you can land on a very foggy day. And the only thing the pilot will do is, if he actually doesn't see the runway, I think the decision altitude is 50 feet. It might be slightly lower than that for Cat 3. And he will then abort the landing. Here you see on the right an ACIS using a variety of much more sophisticated sensors, including LiDAR, to map the environment and choose the path to the ground based on what the sensors and a bunch of different sensors fused information together about what the best place is to land and how to avoid obstructions and obstacles that may be a hazard to the aircraft in the course of landing. So another distinction between automation and autonomy was done by the National Academy of Sciences in a report about 7 years ago that was published talking about autonomy in civil aviation. And I helped actually author this report. And this is a very good primer on the challenges the community faces in creating more autonomy in aviation. It's not just about certifying the aircraft themselves. The other thing is, when we think about automation, we shouldn't just think about automating functions. We should also think about automation as assisting human beings. We all use automation every day to assist us in doing jobs that the automation's not doing the job, but it's making it possible for us to do that job. And there's increasingly sophisticated automation being made available to the flight deck, including electronic flight bags and some work we did when I was at MITRE. We were creating an artificial intelligence augmentation to an electronic flight bag, which would assist the pilot by listening to what the pilot is saying to the air traffic controller, for example, and anticipating what information that the pilot may need and pulling that information up, reminding the pilot of things they might have forgot to do, because the cognitive workload of a pilot, especially without a co-pilot, is pretty high. And we actually called this tool a digital co-pilot. So the other thing is, we can automate functions where the automation, the machine is doing the task and the human is managing and is oversight of the automation, versus the human doing the task with a machine or automation assisting the human. And if you automate the task, there are problems with that, especially if you expect the human to take over if the automation can't handle it. A human being can't land in a Cat 3 situation because they can't see the runway. But if we had a Cat 3 landing, and in the middle of the landing, the automation, for whatever reason, says, I can't handle it anymore, you take over, the human being is not in a situation to take over. And in fact, in aviation, we don't allow pilots to always use auto land because their skills would degrade. And we actually require a certain number of landings per month by a pilot, that they actually perform the landings in order to keep current, because we don't want their skills to degrade. The other thing is of having a human be the backup to automation is they just don't have this situational awareness or even the attentiveness to take over in the event that the automation can't handle it. And a perfect example of this is Air France 447, where the automation was unable to handle the operation because of faulty sensors, and the humans didn't have the situational awareness to take over, and they ended up stalling a perfectly good airplane that had a clogged pitot tube, that was all that was wrong with the airplane. And when the human took over for the automation, the humans then stalled the airplane, and the airplane, over almost a 10-minute period of mistakes, fell into the ocean. Automation, though, doesn't get distracted, doesn't get tired, always is on, always vigilant, can make decisions really quickly, and can use way more data than any human being can handle. So it's the right balance of the two that we should also be thinking about as we evolve systems. So, when we think about the automating the task, it is, what is the role of the human? Is the human in the loop where nothing happens without the human acting, or is the human watching the automation and can make adjustments and intervene, or is the situation where the human can simply they can't make any adjustments, they can simply turn the automation off and abort the landing, as in with the Cat 3? Or is the human totally out of the loop where they have no ability to contribute at all? And an example of this would be an engine FADEC, where the human being has no ability to interact and manage the operation of the engine. It's fully automated, and the human can simply shut the engine off. That's about it. They can't make any adjustments to the fuel mixture at all. They can change the thrust they expect from the engine, but they can't change the fuel mixture or the or any other adjustments. When we look at automated assistance, we might want to think of automation in the same way. Is the human needed? Is the automation needed in order to make the decision? Can the automation take over for the human, and basically turn off the human's ability to act? And we have an example of that today. The military on their F-16s and F-35s have implemented a system called Auto GCAS, which to me is one of the greatest automation systems I've ever seen implemented. It simply monitors the aircraft state, and if the aircraft is seconds away from a collision with the ground, the aircraft automation will disable the ability for the pilot to control the aircraft and totally take control of the aircraft and have it go wings level at a 6-degree climb to avoid a collision with the ground. And that automation has saved over a dozen lives, and that system has won the Collier Trophy, which is the highest recognition in aviation. So I'm going to talk a little bit about operational integration, and just want to remind you there's, excuse me, go ahead. Someone has a question?
Can we go back to the previous?
Certainly.
Yeah, so what you're saying is this, you are interchanging human with automation. So there is no differences between automation on the loop and human in the loop? Is that...
Well, there is a difference, but what I'm postulating or asserting is that we might want to think of, when we're looking at the human versus automation role, we might also, everyone talks about the human being, the phrases on the left are commonly used and discussed, but there are times when we might have automation taking over for the human. And basically, because the automation is the safety net, the automation is essentially turning the human off, as opposed to just the human turning the automation off. So a little bit of tongue in cheek, I'm asking the question, should we be using terms like automation in the loop as well, or automation over the loop? And the Auto GCAS being my example of where the automation was on the loop, so that, well, actually over the loop, where the human was basically turned off and the automation took over for this situation. So it's just a different way of thinking about the systems. Any other thoughts, comments?
Andy, I'm sorry. Can you please repeat the name of this system that you just mentioned? The safety system.
Auto GCAS. Auto GCAS. And there's a YouTube. If you do a YouTube search on Auto GCAS, I think if you put the word Auto GCAS Save or Auto GCAS Aviation Week or something like that, you will see an excellent video of a nose camera and the audio of a pilot. In this case, the pilot screwed up because the pilot passed out. And for those who don't know, F-16s, a lot of F-16 pilots, unfortunately, are lost in training because when they're practicing close air support maneuvers, they have to get very low to the ground. And sometimes they make mistakes and they crash. So this system is used mainly in training so we don't lose pilots and aircraft as well. And it's a training video of a pilot who passes out during the maneuver from the G-forces. He's totally unconscious, and you can hear his instructor, who's in another airplane, yelling at him to pull up as you see the aircraft slowly go to supersonic as it's nose down, heading to the ground. You're looking out the window, listening to the instructor to try to wake this guy up, and then the aircraft pulls up, and the pilot survives. And so it's really chilling. To be quite frank, every time I watch that video, I often show it in talks. It gives me chills. I unfortunately did not pull that one for this talk. Any other comments, thoughts? And I accept tomatoes too, if you want to throw something at me because you don't agree with me. So in aviation, we have a lot of regulations. Some people point out that aviation is one of the most regulated industries there is. We have primarily 3 different classes of regulations that are there to ensure the safety of the entire system. One is regulations about the airworthiness of the aircraft. We have regulations about who is able to fly an airplane or who's even able to operate an aircraft. And there's a difference between flying an aircraft, like a pilot does, and operating an aircraft like an airline does. Now, when a pilot owns an aircraft, they're an owner-operator. But when an airline is actually certified to operate by both the Department of Transportation and the FAA. And so there's a bunch of things that are put in place to ensure the safety of aviation. And then the third class is a bunch of rules about how we fly, how we actually operate these aircraft when the pilot is actually flying, how he's supposed to do his job. And I'm primarily going to focus on that aspect in our talk today. So just a few statistics, and these are operational statistics from pre-COVID. There are lots of operations every day. This is just in the United States. But I want to point out the top line there in that chart is a line showing what's known as IFR, Instrument Flight Rules Operations. And I'm going to talk more about what that is. These are primarily the operations that are being handled by air traffic controllers. And I apologize for that barking dog, but we're under attack by the UPS man right now. So the dog is defending the homestead. The aircraft under the control of air traffic controllers are often referred to as IFR for shorthand, and they'll include all the airline operations. Those are all IFR. But there's a tremendous number of VFR operations a day. I think that number might be, yeah, that sounds about right, about 31,000 VFR operations. So the bottom line is there's a lot of operations that are not necessarily talking to air traffic controllers. And that's a lot of operations that we have to think about when we talk about an aircraft that's fully automated, because there's behaviors that those human beings on those aircraft have that they have to coordinate with other human beings through the rules. that they follow, and some of them can be complicated. I do want to also point out that when we look at some of these new aircraft, we have to acknowledge that aviation is a huge part of the economy, and I know there's a lot of people with ideas about all these new technologies like unmanned aircraft delivering pizzas and all these new business opportunities and commercial opportunities, but we don't want to disrupt the rest of aviation, which is very important. And as many of you know, the aviation community is suffering right now because of COVID. So let's talk about airspace. When we look out the window, when we look up, we just see sky. But airspace is actually subdivided into different classes of airspace that have different rules for how you are to operate in that airspace. And different aircraft that we're imagining for the future, and these new entrants want to operate in different kinds of airspace. So we have aircraft like high altitude, long endurance aircraft that want to operate at very high altitudes. They need to fly from the ground to get to those altitudes, so they have to go through all this airspace, but they want to operate sometimes for weeks or months at a time at very high altitudes in what's often known as upper E or E above A. It's Class E airspace that's above Class A airspace. And the FAA actually has an ops concept of how that might work in the future. Today, the only aircraft that are flying at those altitudes are military aircraft, but there's commercial aircraft that want to routinely operate in that airspace. There's other aircraft that people are building that are going to be highly automated or fully automated or fully autonomous that want to operate just like every other airplane. There's a company called X-Wing, which is building a small cargo aircraft. They're actually modifying a Cessna Caravan to be pilotless and not require a pilot. And they are going to be flying and landing at airports with other aircraft and operating just like everyone else, but just not have a pilot on board. Then there's small UAS, and I think everyone's talking about those, and they tend to fly at much lower altitudes, and people want to do things from delivering packages to doing security or land surveys, search and rescue. You name it, there are people with ideas of how to use small unmanned aircraft. And typically these are at pretty low altitudes. And they have a challenge because they want to be able to operate beyond visual line of sight of the pilot. And I'll talk more about that in a minute. And then there's the urban air mobility. And these aircraft want to fly, at maybe below 5,000 feet, but they basically want to, in order to fly the missions they envision, they're going to fly in all classes of airspace, and they're going to interact with basically all of aviation operations, including small UAS operations. And I'm going to talk about some of the challenges to making all of this a reality. I'll pause here, see if there are any comments or questions. Okay. So small UAS operational integration. There's a lot of operational capabilities that are needed in order to make this a reality. And when I first started working on operational integration of unmanned aircraft, they weren't allowed to fly at all. They were only allowed to fly on an exception basis, and there was no way to fly an operational or to operate a commercial unmanned aircraft. So you couldn't operate for commercial purposes. That was a challenge. In order to make money, you have to be able to operate not in basically all classes of airspace, even at the surface. You need to be able to cross roadways. You need to be able to operate at night. A lot of operations, a lot of applications will require the ability to operate beyond the visual line of sight of the pilot. And then ultimately, we want to get to the point where a single pilot could be responsible for more than one flight at a time, so that you can scale the operations, out of economic necessity. And I want to emphasize I'm just talking about small. These are things, the FAA defines small unmanned aircraft as weighing 55 pounds or less. Actually, I think that's in legislation. It was defined as 55 pounds or less. And there's a lot of different missions that can be done. You can do aerial photography in visual line of sight of the pilot on the ground, but you could do more aerial photography if you get these other operational capabilities. Some capabilities like linear inspection, if you want to do linear inspection, you're going to need beyond visual line of sight capability. Otherwise, you can't inspect, you can't inspect a power line if you can only inspect the power lines as far as you could see them from the ground. And you certainly can't do package delivery without the ability to operate beyond the visual line of sight of the pilot on the ground. And in order for them to make money, you're going to need a single pilot to be able to handle multiple aircraft. So my crude cartoon way of showing the alignment of the missions and the utility of the missions with the capabilities are where the lines align. So hopefully you understand what I'm trying to show there. And then you got to look at the challenge. If you want to operate for commercial purposes, the real challenge is there were no rules that allowed it. Well, the FAA eventually established the Part 107 rule in 2016 that allowed small unmanned aircraft to operate commercially. I actually was heavily involved in the development of that rule from its inception. And I started working on the small UAS rule in 2006. So it took 10 years to get that rule completed. It's not perfect, but you needed a mechanism to be able to coordinate, because the rule required coordination if you were going to operate in the surface area of Class B, C, D, and E airspace. And that's basically airspace that's around airports. And that's everywhere. And airports tend to be where people are. And so 5 miles of around most airports is what defines the surface area of Class B. I live within 5 miles of Dulles Airport. I wouldn't be able to fly an unmanned aircraft at my house without a mechanism to easily coordinate that. And the FAA established LANCE in 2018 to do that. Then there's the risks of operating over roadways and at night. That wasn't allowed. The FAA issued some new rules that enabled that to happen, and that happened just last month. The FAA published a final rule for those. And then the ability to operate beyond visual line of sight. Well, you still can't operate beyond visual line of sight without an exception. And the FAA has granted a few exceptions, but it's not routine. And that operational capability really doesn't exist. There's a few people who've gotten special permission to do it, but it's in a very limited fashion, really in a learning mode fashion. And in some cases, they require visual observers to do it. And one of the key capabilities that's needed is something called detect and avoid. But detect and avoid alone is not going to allow you to operate beyond visual line of sight. You need a lot of other things ultimately to make that happen. So I'm going to talk a little bit about enabling beyond visual line of sight operations, but I'll pause on this crude chart to see if anyone had any questions or comments.
Andy, are there actually any unmanned aerial vehicles flying in the airspace right now?
Yes, there are literally thousands. Small UAS are unmanned aircraft. They're aircraft. In fact, there are more registered unmanned aircraft in the FAA's database than all the other aircraft combined. So there's lots of unmanned aircraft that have the ability to fly. At any given time, the FAA really doesn't know how many are in the air because we don't have operational data on when they operate, the small ones. The military routinely operates unmanned aircraft in the U.S. airspace, and they have been for 20 plus years. But they do that they have operational limits on how they can fly, and they often have ground augmentations that ensure the safety of the operation by monitoring the airspace. And then there's a bunch of kind of exceptions and waivers that the FAA has granted for us to kind of learn. So there is, for example, limited delivery being done in Virginia, actually not too far from you guys, in Christiansburg, Virginia, right next door to Virginia Tech. Google is doing delivery with drones. They very limited geographic area. They're able to deliver things like medicines from CVS. There was a couple other books from the library, a few other things that are delivering. So there's limited, but it's not routine for the delivery.
I was referring to large scale, like aircraft type of UAS.
Well, even a small UAS is an aircraft by the FAA's definition. You're talking large. The military operates the Global Hawk. NASA operates the Global Hawk as well. The Global Hawk has a wingspan the size of a 737. It's pretty big, and they operate routinely out of Beale Air Force Base and out of Grand Forks Air Force Base in North Dakota. And the Global Hawk flies a very predefined route, has a bunch of contingencies if it loses, if it has a mechanical problem or it loses link. It has a bunch of pre-programmed contingencies for every point along its flight path. The Navy is also operating their variant of the Global Hawk, and I forget actually where they're operating out of. But that's happening routinely, and I've watched flight ops of the Global Hawk and the Predator as well. So so they and the military is mostly operating in the United States for training. DHS and the Coast Guard operate operationally out of the U.S. as well.
Thank you.
Does that help?
Yeah, thanks.
Now, commercial large UASs, there's not any commercial operations of large UASs that I am aware of.
Okay. Thanks.
So operating beyond visual line of sight, I'm going to use a construct that the KO developed. They called it their conflict management or approach to conflict management. And they've defined 3 layers: a strategic deconfliction layer, which even pre-flight will work to reduce the need to make tactical adjustments. There's a tactical separation layer, which ensures that aircraft don't get close to each other to present a risk. And then collision avoidance is a much more last-minute effort to avoid 2 aircraft colliding. So strategic deconfliction is really to help kind of balance the ability to do tactical separation. Strategic deconfliction would also include capacity demand balancing. Tactical separation will keep aircraft well clear, and collision avoidance is trying to avoid a mid-air collision or a near mid-air collision. And when you're looking at this, you really have to look at the airspace in which you're operating. You have to think about the ambient traffic in that airspace. And then there's procedures which we can use to ensure aircraft is strategically deconflicted. A procedure example that I can give you is if you were an unmanned aircraft that was surveying power lines to look for problems with power lines, and you flew your unmanned aircraft really near the power lines, you're probably not going to encounter other aircraft because aircraft don't like to fly near power lines because power lines are dangerous to aircraft. So if you're a small unmanned aircraft flying near power lines, you're procedurally deconflicted from other aircraft. and that's known as shielded operations. And it's actually, New Zealand has regulations to do that routinely. Then there's technologies on the ground that could help with both strategic deconfliction and tactical separation. And many of you might have heard of UAS traffic management, which is a air traffic management capability and automation to coordinate operations among UAS operators. There's the ability to surveil the airspace with ground surveillance radars. This is primarily how the military deconflicts their aircraft from other aircraft in the airspace. And then there's technology that you might use to cue the pilot on the ground, that including from sensors on board the aircraft, that the pilot should maneuver his aircraft because the sensor on board the aircraft is sensing another aircraft in its vicinity. And then there's aircraft-based capabilities, and these tend to be automated because they're on the aircraft. And since there's no human being on the aircraft, there's only automation on the aircraft. The sensors and the decision-making capability automated on the aircraft is the one that's doing the deconfliction, whether it's tactical separation or a collision avoidance maneuver. And there's a lot of technology being developed there. And people are involved, so we also have to think also about the role of people in all of this as well. And I think this group, you guys, I would think, are pretty knowledgeable about advanced air mobility. There are a number of players here. Can I assume a knowledge of advanced air mobility among this crowd? So I'm not going to go in detail. Most of them are envisioning a VTOL aircraft that's electric powered. Most of them are hoping eventually to not have a pilot on board. They may start with pilots on board. But an example would be it's very complicated to fly a aircraft that uses multi-rotor thrust to control and steer the aircraft, especially in its vertical flight. And a lot of these manufacturers who are even envisioning a pilot on board are talking about something called unified flight controls, where the pilot is steering the aircraft. They're not actually controlling any avionics control surfaces or aviation control surfaces. So they're not controlling the variable thrust in the rotors to control the aircraft. That wouldn't be possible. And this unified flight control is in the F-35 has unified flight controls. So no matter what speed the F-35 is going, the pilot is exerting the same inputs to control direction and speed. And most of these are envisioned to be mass produced. But they got to operate in the airspace with everyone else. So there's a lot of challenges in how you would do that. If you don't have a pilot on board, there's different challenges than if you do have a pilot on board. If you have a pilot on board, you probably could follow most of the airspace procedures as they exist today. If you don't have a pilot on board, you can't. And that's where a lot of these operational integration challenges arise, is when there's no pilot on board. But some of them, like weather, doesn't change whether you have a pilot on board or not. These aircraft are going to be operating in areas that we typically don't have aviation operations today, so there's no weather sensors. And more importantly, the micro weather conditions, especially winds around buildings and visibility, could be a real challenge. Anyone who's walked in a city knows about the winds in an urban canyon. And if you try to have an aviation operation that is trying to land around buildings, there could be real eddies and wind shears in the vicinity of structure. And we're going to need, even with a manned aircraft, an ability to deal with predictions and both where that wind is and how the approaches should be set up to avoid those wind eddies. So I'm going to briefly talk about visual flight rules versus instrument flight rules. Visual flight rules are built around the ability for the pilot to operate the aircraft using their eyes. Instrument flight rules are procedures built around the ability of an aircraft to be operated by a pilot by looking at technology, looking at automation. So with visual flight rules, the pilot has to see. So there's weather requirements called visual meteorological conditions. So you can only fly VFR in VMC. You can fly IFR in VMC, but you can't fly VFR when the weather is such that you can't actually see. And there's rules about cloud, the distance that you could see. That's the visibility, the height of the ceiling, and you have to stay away from clouds when you're operating VFR. IFR, you have, well, let me just make a comment. The VFR, one of the advantages of VFR is it's very flexible and scalable. And a lot of pilots fly VFR because it's flexible. It's very easy to do. So if the weather is good, like it is here in Virginia, if I was to go to the airport today and get in an aircraft to go fly, it would probably be as a VFR flight unless I was required, because of the airspace I'm operating in, to be VFR. So IFR is actually required in certain airspace classes. You have to talk to the controller. And that's one of the key distinction, is that in an instrument flight rule, the pilot is talking to air traffic control, and he's receiving radar separation services from the air traffic controller. They have to file a flight plan. They have to do what the controller tells them to do. They can use instruments to navigate, but the controller is telling them and giving them clearances. And they must be what we call talking and squawking to that controller. They have to be in radio communications with them, and they have to be transponding their location to the radar inquiries, or using ADS. Well, now they have to be using ADS-B. And if it's instrument meteorological conditions, you have to fly IFR, and if you're in class A or B airspace, you have to fly IFR. And the separation requirement for IFR is, depending on what airspace you're in, between 3 and 5 miles, and that's quite a far distance for aircraft to be separated. The nice thing about IFR is it doesn't matter what the operating environment is, you can operate, and it's very predictable. You know what's going to happen. VFR is really a self-organizing system. It's distributed decision-making, where the decision-making is all in the hands of the pilot on each individual aircraft. There's rules they have to follow, but it's self-organizing within those rules. IFR, on the other hand, is centralized, and there's strategic and tactical deconfliction services being provided by the ground, which is effectively choreographing the operation. And they're doing that based on known intent. Neither of these fit the advanced air mobility paradigm, and that's the challenge. And so a hybrid approach that kind of takes the self-organizing aspects of VFR and the distributed decision-making of VFR, together with the sharing of intent and centralized coordination through information sharing of IFR, and creating a hybrid approach. When I was at Boeing, we had a ConOp that looked like this, and folks at NASA and the FAA are talking this way now. These rules don't exist today, but this is what's going to be needed in the future to enable highly automated flight without humans on board. NASA calls them digital flight rules. In the interest of time, I'm going to skip this chart. How much more time do we have?
You have 10 more minutes.
Oh, okay. Just so you know, there are predefined routes that helicopters fly. Anyone who's been annoyed by helicopters are annoyed, then they look up and they're like, that helicopter's always flying over there. Well, very often the reason they're always flying over there is because there's defined routes, even in busy airspace, for helicopter operations. And what I'm showing you is a map of the airspace in Northern Virginia. I don't know if you can see, I can get my pointer. This is actually Dulles Airport. And my house is like right here. And so Dulles Airport, National Airport is over here. And these are showing, these different shaded areas are showing different types of airspace. This is actually the surface area of the Class B airspace around Dulles Airport. And these lines here are the helicopter routes. Many helicopter routes follow roads. Why do helicopter routes follow roads? It's not for noise abatement. It's because the helicopter pilots use the road for navigation. They look at the road and they follow the road, and that's how they navigate. So this is, they actually named this helicopter route after the road it follows. It's called the Route 7 helicopter route. Really catchy name. That's Leesburg Pipe, otherwise known locally as Route 7. Many cities have a set of helicopter routes around the city. This helicopter route, wavy and all that, it's because it follows the road. This is actually the Capitol Beltway around DC. There's a helicopter route right over the Capitol Beltway. And these helicopter routes, even though they're going through Class B airspace, they're not necessarily getting air traffic control separation services. They're getting cleared to be on the route, and then the controller is not paying attention to them as much. The controller is separating other aircraft from the route. They're not necessarily receiving the same services. So we are already starting to do this with how we manage rotorcraft in many cities today. And this is a list of the cities that have those routes. I have to get rid of my pointer in order to see. Another thing, I don't know if you've heard the term Mode C Vale, but there's a block of airspace around major airports, all of the airports with Class B airspace, 30 nautical miles around that airport. That's quite a distance. You are required to have ADS-B in that airspace. So all the aircraft in that airspace are participating in ADS-B. That's not true in much of the airspace around the country. You're not required to have ADS-B, but if you're in the Mode C Vale or in Class B airspace or Class C airspace, you must have ADS-B, as well as if you're in Class A airspace. So there's a advantage operating in the Mode C Vale because as an unmanned aircraft, you know where all the other aircraft are because they all have ADS-B. Unmanned aircraft can't have ADS-B, but all the manned aircraft will. And this shows Denver. The entire city of Denver is in the Mode C Vale. Even though the airport is out in the prairie further east, the entire city of Denver, you can see the circle here. This is the Mode C Vale. It's all in the Mode C Vale. And so you would know where the aircraft are. And it just so happens that the majority of the US population lives in the Mode C Vale. And so if you can use ADS-B as an input and a monitoring tool for automated aircraft, you will know where all the manned aircraft are.
Sorry, Andy, what is an ADS-B? I might have missed it.
Oh, ADS-B is a technology that is mandated, I forgot the year, maybe it was 2018. Every aircraft that operates in certain, like the Mode C Vale, in Class B airspace, has to have a technology on board the aircraft that once a second transmits their location. And a little bit of identity information. and it broadcasts it out. So it transmits it to the ground, and it could be used for separation services by air traffic controllers, and it broadcasts it to all the other aircraft around it as well. And you could have ADS-B in that you could display in your aircraft the location of all the other aircraft around you.
How manned aircraft are being localized? Is it true what they say that the planes that we fly do not have GPS?
Well, ADS-B requires GPS. So if you have ADS-B, you have GPS, and it's often built into the ADS-B avionics for general aviation aircraft. So the general aviation aircraft might not have been originally equipped with ADS-B, with GPS, but if they install ADS-B, it has to have it. And there is one vendor who literally makes a light bulb that you could take the landing light or the anti-collision light out of its enclosure, screw in this new light, and it has built-in ADS-B into the light. So it's totally self-contained, and you can effectively install ADS-B that way. So there's also special rules. There's a special procedure in LA that you can literally fly over the top at 3,500 feet and 4,500 feet over the top of LAX and not be talking to an air traffic controller if you're following a set of procedures in that airspace. Normally, if you were in that airspace, you'd be required to talk to an air traffic controller, but if you follow this set of procedures, there's no need to talk to an air traffic controller. So I'm simply using these as examples of where we're trying to find a way to distribute decision-making, even in very complex environments, to the pilot and distribute decision-making to the edge. I'm going to skip this page. Just a final thought on AI and where it might be appropriate. There's a lot of functionality which we might automate on an aircraft, everything from the flight stability of the aircraft to how the aircraft picks its path through the airspace and manages its path through the airspace. We can have an aircraft that the automation is just on flight stability, and the pilot is steering it and choosing where to fly. And the best example I have of this is a prototype aircraft that Kitty Hawk made called the Flyer, which was a highly automated aircraft. The pilot steered it, but the pilot could not stall the aircraft. They couldn't flip it over. They actually had a geofence that they couldn't even leave a geographic area. Automation controlled that, but the pilot chose where to steer it, and to avoid bumping into other aircraft. Depending on what functionality is being automated, flight stability is very well defined, structured decisions defined mostly by physics. As you move to the right, these become less structured decisions, and the decision automation associated with those, if you are going to automate those decisions, they become more and more complex, requiring more reasoning and judgment to be made. And so when you're looking at where is AI fit, well, you don't need AI for flight stability. But as I get more and more sophisticated, I may need AI-based algorithms for these more sophisticated operations. And that may be the only way to deal with the reasoning and judgment and the perception required. And when we're looking at operational integration, it's not going to happen overnight. We're not going to jump to having fully automated aircraft in our system. We are likely to have pilots on board eVTOL aircraft. And that's actually Joby's Aviation's plan, is they're going to have an eVTOL aircraft that has a pilot on board with unified flight controls. And there's a lot of challenges even to just make that a reality. We're talking about an electric aircraft. We're talking about the unified flight controls. We're talking about thrust-based flight control. all of that would need to be certified. And we're going to just have different steps along the way dealing with the integration challenges. And maybe we could talk about this in more detail later, but that I just wanted to put on the table that when we're looking at operational integration, we shouldn't be thinking about it as a single step. We should be thinking about it as a phased approach to operational integration. I'm going to skip this slide, and I'm going to just close with a little bit of a commercial. I work for a company called Noblus. Noblus is a small, well, small compared to, I used to work at Boeing, which was really big. Small in that we're only 1,300 people. But we're a nonprofit company doing science and technology for the federal government. And we have a internship program, and we are looking for interns. Our internship program actually received an award last year as one of the top 100 internship programs in the United States. We're hiring 75 interns for our summer this year, and I would strongly encourage folks to apply. My contact information is on the next slide if you want more information, or you can get more information on the link. And I think Stacy is distributing these slides, so the links will be there. And that's all I had. I'm happy to answer any questions people didn't interrupt me for.
Okay. Thank you so much, Andy. Thank you so much.
I love to talk about this stuff.
It's just something also for everyone to know. Andy, are you still part of advisory board for ULI at Arizona? Is that right?
Yeah, I'm also on the National Academy of Sciences advisory board for. They have a board that the NASA Aeronautics has established called the Aerospace and Space Engineering Board, and we have the ULI is something that that board has been very interested in as well. We're actually doing a study on the ULIs right now, about to be published.
All right. Thank you. Okay, now the floor is open for colleagues on the cyberspace to ask question from Andy, please. Okay.
Or tell me where you don't agree with me. I would love to hear that too.
Okay, to that I'm going to refer to Jim, Mehran, and Bruce. If they don't say anything, it means they agree with you.
Hello, Dr. Andy. I'm Rabbi, fourth year PhD student. I have a couple of questions on your presentations.
Sure.
At first, I would like to go to the slide number 12, where you have discussed layered approach to enable BVLOS. Here you have talked about ground-based technical capabilities. So I wanted to see that you have make it the shared of strategic deconflictions and tactical separations. I do understand the relation with tactical separations with the ground-based technical capabilities, but I wanted to know that what are strategic deconfliction that you would like to refer for ground-based technical capabilities. This is
my opinion is UAS traffic management is a strategic deconfliction capability, and it's a ground-based automation that is doing strategic deconfliction. Now, there are some people who think it eventually could be used for tactical, but the way it's coming out, and I'm on the standards committee for the UAS traffic management standards group. The first version of the standard, it will only be strategic in its capability. So does that help you, Robbie?
Yes, thank you for your opinion. And I have another question from slide 7, where you have discussed that human-centered control system. So there is a trade-off that how much accuracy we want to get from the system, that system consider human in the loop system. But the problem is that if human is in the system, then human fatigue and tiredness also affect the system. So how your research perceptions that can handle these situations? Do you think that human in the loop system can be the best, whereas human has some limitation?
Well, again, there's no one answer, one being better than the other. It's designing the system for the desired effect. There's a whole body of work now that's broadly being called human-machine teaming, and designing the allocation of responsibilities between the machine and the human to have the desired operational output is what's critical. And so there's some situations where, I'll give you an example. Laser eye surgery, we have that's a very highly automated process. I don't think any of us would lay down for laser eye surgery with a human being holding a laser poking in our eyes. We lay there, and a computer does the carving of our and fixes the lens of our eyes by carving the eyes with the laser. That's a highly automated. It's very predefined and deterministic, but it's highly automated that we trust automation to do. But there's other things that I don't know that I'd want to rely on automation to fully handle. I believe that's why we still have human beings sitting as judges in court and making decisions, because they have the ability to perceive the situation and make a good judgment. So it really depends on the function being defined. Does that help, Robbie?
Yes, thank you for your answer. Yes, my question is finished. Thank you for your patience to provide sufficient explanations for my questions. Thank you again.
Hey, thank you.
Andy, I have a question, but I do not want to monopolize the questions because I already asked. If there is no one, I'd like to ask something about slide 17, please. And perhaps even slide, no, it's fine. So in this, you're having intersecting routes for the helicopters. How do you guarantee that the two different helicopters are not going to be at the same point at the same time?
Well, first of all, we don't guarantee anything in aviation. It's within acceptable level of risk, first of all. And I'm not exactly sure all of the helicopter procedures in the Washington, D.C. area. Sometimes they'll clear someone on the route to an intersection point, and then they'll re-clear them for the rest of the route. Other times they may clear them for the route, but depending on the directions they go, there may be different altitudes. So, for example, if you're heading east to west, you might be at one altitude, and if you're going if you're going east to west, you're in one altitude, and west to east at another altitude, so you're not head-on on the route. As far as the intersection, we also rely on people still to look out the window. You have to, a pilot is required to remain well clear of other aircraft at all times, so they still need to be looking out the window, even if they're on an air traffic control clearance. How they specifically handle it, I'd have to actually read the procedures that they have, but they probably have a procedure for that.
Do you have similar aerial corridors intersecting in aircraft and commercial flight airplanes?
Oh, absolutely. And that's what the job of the air traffic controller is they are, we have routes, and I don't have a map, but they call them the jet routes in the airspace. Our airspace, if you sit outside and lay on your back on a clear day, you see the contrails of the aircraft, and they fly the same route all the time. And then the wind blows the contrail slightly off, and you see these moving lines that are blowing with the wind, but the planes are on the same route. It's because there's a jet route that aircraft is flying on, and the aircraft on the jet route is flying the same route as the aircraft in front of it. And so the air traffic controllers use those jet routes. That's the way the aircraft are organized. And so they have to deal with aircraft at merge points. They have to deal with aircraft, that one might be flying faster than another. And they call those overtakes. And so that's one of the jobs of an air traffic controller, is to keep aircraft safely separated on those jet routes. And if they fail in their job, there's a technology called TCAS, which will alert the pilot on a maneuver they should make to avoid a collision. And TCAS is again, this is a perfect example of human in the loop. TCAS will simply tell the pilot what to do. The pilot is told always to listen to TCAS, but the pilot is required to do something. But if they don't do what TCAS says, they're usually in trouble.
So at every point that an intersecting route exists, it is fair to assume that there has to be an entity that regulates the traffic.
Well, I'm sure you've driven on roads where every intersection doesn't have someone regulating the traffic. There's not a traffic light. There's not a cop on the corner. There might not even be a stop sign. And so we have intersections. We don't need regulation because the risk of a collision on the ground, I'm talking about on the roads, is such that it's a low probability, and we rely on the drivers to separate. And we do the same thing in aviation. If there's a higher risk of problems, we then have to have someone choreographing those operations. But at many airports, most airports in the United States, we don't even have an air traffic controller. Now, only the busy airports have air traffic controllers who decide whose turn it is to land and how to organize the aircraft. But there are many airports that don't have a lot of operations. They don't have a manned air traffic control tower, but there's procedures for calling out on the radio that you're about to land, which direction you're landing. There's a pattern of flight around the airport. There's even a requirement to fly next to the airport first before you land to make sure that there's no one else maneuvering on the ground. And so you have awareness. So all of these things, this is what I mean about self-organizing. That self-organizing approach is very scalable. Could we use automation to have a self-organizing approach that won't burden our system with someone in a centralized manner coordinating everything? And automation can help us do that.
Thanks, Andy. It was a very nice presentation.
Yeah, it was fun.
Yes, with that, if there is no, I'm going to thank Andy, and I hope we will have our meeting soon, and I will let you know. But thank you so much, everyone.
Enjoyed it.
Good weekend.
And if anyone has any follow-up questions, my email's available. Happy to follow up.
Yes. Okay. Thank you so much. Thank you.